Here's a problem where we're using bar charts to show how energy changes forms and also changes quantities as a result of work, and we're using a bar chart or set of bar charts to do that. This one actually gives us some numbers. That's not always the case. Sometimes we're just showing sort of a change, relatively speaking, and trying to show, you know, without actually doing a lot of calculation. But this time we do have numbers to work with. And the situation is that we have a 100 Newton box. That's a FG they're giving us there. It's already above the ground when we start out here, 1 meter above the ground. And then it's already rising when we start paying attention to it. And then the student pushes even harder, I guess, than she was to begin with, and accelerates it up because we can tell this vertical force is now larger than weight. It's going to speed up, right? So now it's going to experience a gain in kinetic energy too as it rises up into the air. So we're supposed to show this bar chart before and after the box moves upward a distance of 1 more meter. So it's going to go up to a total height of maybe 2 meters up here. So it's going to be displaced, and work is being done by this upward force. And we're considering our system to be the Earth and the box. That's important because that's why we're talking about gravitational potential energy, and we're saying that the gravity is not doing any work because gravity would be a force internal to the system. So work is only done by outside forces. Also notice that this is from typers, and so they're calling kinetic energy KE, and they're referring to potential energy with PE instead of U, like your book would use UG here, and your book would use for the spring US. So these quantities, oops, this would be noted differently in your book. So we're gonna do some calculations here. We have the gravitational potential energy we know is calculated by mgy, and so the initial gravitational potential energy would just be Fg times the initial height here. So 100 newtons times 1 meter would be 100 joules. So on this scale, it looks like it would be kind of like that size, 100 joules. We don't have any springs involved here, so I'm kind of just like leaving that as an X. And then work, let's calculate the work done by this force. So if I'm doing my external, this is a constant force, so I get to just do force times displacement times cosine theta. The force is straight up, the displacement is straight up. So I can, the theta is 0 here, and I get to just do 120 newtons times 1 meter of displacement from here to here. So that's going to be 120 joules. So I'm like, you know, slightly over the 100 line. Okay. So got that and that. Okay, so that tells me that total here, I expect the initial energy plus the work equals the final energy. So I've got 500 plus 100 plus 120 worth of energy that I need to account for in the final state. So that's 720. Okay, so now the potential energy final is really easy to calculate because I know that the box is now 2 meters above the ground, and I've got, so now UG, here's UG again, is now 200. So I'm going to come up here to the 200 joules. There is no spring energy still. So then I can just use subtraction to figure out what's left, and that must be kinetic. And that's going to be 520. So 1, 2, 3, 4, 5. So I have a slight increase from what I had before, which makes sense because as this person is pushing, that 120 newtons is slightly more than the weight of the box, so this box should be accelerating. It should be increasing its velocity, which would increase its kinetic energy. Okay.